sheet, you see 3 right triangles. In each of the triangles, we're given 2 sides, and we're missing the third. So the legs are A and B, but it doesn't matter which is which. And then the hypotenuse would be C. So for this first one, if we use the Pythagorean theorem, 8 squared plus 25 squared equals C squared. So if I calculate that, 8 squared plus 25 squared is 689. Now what do I do? Square root it, and I'm lazy, so I just raise it to the 1/2. So I just push exponent 0.5. So C is 26.24. But wait a minute. If we square root C squared, shouldn't we do plus or minus? We should, but you can't have a negative side length yet. That's just a preview for the next chapter. It turns out in the next chapter that like 1/3 of all of the side lengths are negative. Yep. There's kind of a catch to it, but it is possible to have a negative side length on a triangle. Now, that doesn't mean that negative side lengths exist out in space. But in trigonometry, we use negative side lengths all the time. And actually using them allows us to do things that we couldn't do otherwise. So stay tuned. You'll see negative side lengths later on. Okay. So the second one, I'm missing, say, B. 8 squared plus B squared equals 10 squared. This is a little bit different. So I have 64 plus B squared equals 100. Now what do I do? Subtract the 64. So B squared equals 36, and if I square root that, I get 6. Or, later on, -6. And you actually have to decide which it is, because it could be 6 or it could be -6. Not both, but one or the other. All right, I'm going to pause the video. You guys go ahead and solve the third. All right, when you solve this one, you should get the square root of 208, which is 14.4. All right, now good old Pythagoras, he was a good guy. He didn't come up with the Pythagorean theorem. It was around a lot longer way before him, but we're a little unsure if the other people knew that it always worked. They certainly knew that some Pythagorean triples existed, like a 3, 4, 5 triangle made a right angle. So when the Egyptians built the pyramids, they probably made right angles at the base of the pyramid by using a Pythagorean triplet. They'd take a big long rope that was 300 cubits on one side and 400 cubits on another and 500 cubits on the other. And if you stretch out those ropes and make a triangle out of them, then the one angle is a right angle. That's probably what they did. Now, they knew that there were lots of triangles where there were nice angles that made right angles, but we're not sure if they knew that a squared plus b squared equals c squared for all triangles, even the ones that don't show up as nice numbers. But Pythagoras figured it out. So I guess that's why we name it after him. So for the next one, the Pythagorean theorem relies on 2 sides of a triangle to find the third. What if we only know one side of the triangle? How can we find the lengths of the other 2? Is one side of a right triangle enough to figure out the other 2? No, because how many right triangles are there with a leg equal to 6? An infinite number. Okay, so what else do we need? A second side would allow us to use the Pythagorean theorem. But if I don't know a second side, all I really need to know is how big the triangle is. the shape of the triangle. That's all I need. So if I gave you one angle, let's say this is a 70-degree angle. Now, it doesn't look like a 70-degree angle, but never trust a picture. Always trust the numbers. I now know the shape of the triangle. It's a 20, 70, 90 triangle. And every 20, 70, 90 triangle has the same relationship of the sides. And the relationship of the sides is called trigonometry. So for every trig ratio, like the cosine of theta is equal to a over h, we need an angle, we need an adjacent side, and we need a hypotenuse. So this is basically a function with 3 variables. If you know 2 of those variables, you can use algebra to find the third. So now, if you look at my right triangle, I have what side length? I know the opposite, and I know the angle. I can use trigonometry to find the other 2 sides. So let's call this adjacent, and this is hypotenuse. I put my theta there. I very well could have put my theta on the other side if I would have found out that it's 20. So it doesn't matter which angle you use. How am I going to calculate the length of the adjacent? Well, I need to pick a formula where 2 of the 3 unknowns are listed. So what trig ratio do you want to pick? I know one side, I know the adjacent side, so it's got to either be cosine or tangent. Or sorry, I'm wrong. I know the opposite side. So it's either sine or tangent. Which one am I looking for? I want to know the adjacent, which means I have to pick tangent. So the tangent of the angle 70 degrees is equal to 6 over the adjacent. Is that a multiply or a switch problem? It's a switch problem, so I'm going to switch places with those. Adjacent equals 6 over the tangent of 70. 6 divided by the tangent of 70 is 2.81. Does that number seem reasonable? It's not very big in comparison. But this length looks longer than 6. Don't trust the picture. This angle is 70, which means that angle is 20. So 70 is quite a bit different from 20, so the 2.8 should be a lot different than 6. Okay? What if I would have moved theta to the other side? So I would have had a 20 here and a 6. What would the name of that side be? Opposite. And what trig ratio would I use? Tangent, because I still have O and A. The tangent of 20 is equal to opposite over 6. Is that a switch or a multiply? Multiply. 6 tangent of 20 is the same number. Oh, I wrote it backwards. 2.18. So there are lots of ways to solve these. You can pick any angle you want, but whatever angle you pick will dictate your sine, your cosine, and your tangent. Yeah. So now we need to find the other side. How am I going to calculate the length of the hypotenuse? You could use a Pythagorean theorem, or you could use sine or cosine depending on what angle you pick. So we now know these 2 sides. If you want your answers to be like the one I have, I recommend you not plug that number in your calculator. Now, it doesn't really matter. As long as your answers are within a little bit, I'm going to mark it as correct. But this number here has been estimated. It's been rounded off. So if you type in 2.18 divide the cosine of 70, let me show you. So 2.18 divided the cosine of 70. That's going to be a little bit different than setting up the sine. The sine of 70 equals 6 over the hypotenuse. Is that a multiply or a switch? So 6 divided by the sine of 70. They're going to be a little bit off because 2.18 is not the exact answer. So if you like nice, pretty answers that match mine, use the numbers that are whole numbers. It doesn't really matter though. If you prefer the Pythagorean theorem, go ahead. So the Pythagorean theorem, 6 squared plus 2.18 squared, raise that to the 0.5. You'll notice that's pretty close. Okay? So, you have 4 problems down here. Let's do a couple of them together. This is my adjacent side, and this is my opposite side. What trig ratio am I going to use to calculate the opposite? The sine of 78 is equal to opposite over 4. So 4 sine of 78 is 3.91. Another reason why you would want to use the 4 again and not the 3.91, if you made a mistake and 3.91 is not correct, and you use it to calculate the other side, there's no way to get the right answer, unless you make 2 mistakes that cancel each other out. I guess that's theoretically possible. All right, how are we going to calculate the adjacent? Cosine. So the cosine of 78 equals adjacent over 4. Is that a switch or a multiply? We did the opposite. 4 cosine 78, 0.83. Does that number make sense? It's not very big. But how do I know that that number is probably right? So this angle would be 12. So the 78 and the 90 are really close in size. So the opposite and the hypotenuse should be really close in size. And the adjacent should be a lot smaller than both of them, which is exactly what we see. All right, next one. I don't know the opposite and I don't know the adjacent. How am I going to calculate the opposite? X over 10 is equal to the sine of 45. Multiplier switch. So 10 sine of 45. Well, you can call it whatever you want. Some of the worksheets say X, some will say opposite. So 10 sine is 7.07. And that was calculated by doing 10 sine of 45. How am I going to calculate the adjacent? Cosine of 45 is equal to x over 10 times by 10. 10 cosine of 45. Uh-oh, what'd I do wrong? Why not? Not equilateral, you're close. Isosceles. How do I know that the opposite and the adjacent are the same length? Because the two angles are each 45, so the sides opposite those 45s have to be the same size. Which is interesting. One of them was calculated using 10 sine of 45, and the other was 10 cosine of 45, which means what? The sine of 45 and the cosine of 45 are the same number. That's the only time where O over H is equal to A over H. When the O and the A are the same, which is an isosceles right triangle, which happens when the angle is 45 degrees. So what is the tangent of 45? So the tangent of 45 would be O over A, which is going to equal 1. So if I type in the tangent of 45, I should get 1. So in an isosceles right triangle, the sine and the cosine have the same value, which means that the tangent is 1. But wait a minute. The tangent is O divided by A, which is the opposite side divided by the adjacent. But watch this. What if we took O over H, which is the sine, and I divided it by A over H, which is the cosine? So this is sine over cosine. How do you divide two fractions? You flip the second one upside down and multiply. H over A. The H's cancel. So the tangent is actually the sine value divided by the cosine value. Yes, every single triangle. So we could write the tangent as the sine over the cosine. And we could also write the sine in terms of the cosine. If we had, so let's say this triangle, that's 35, so this would be 55. The sine of 55 would be A over C, right? But that's equal to the cosine of 35, which is also A over C. No. So the sine of 10 is equal to what cosine value? Well, if 10 is on one side of the triangle, what's the other angle? 80. The cosine of 80. Let me show you. The sine of 10 is 0.17. The cosine of 80 is 0.17. So, in general, the sine of theta is equal to the cosine of 90 minus theta. So whatever angle you're looking at, if the sine button is, if the cosine button is broken on your calculator, then you could just do 90 minus theta and then push the sine button, which means the tangent of theta is sine over cosine. So sine is equal to the cosine of 90 minus theta. So tangent is really the cosine of 90 minus theta over the cosine of theta. And what I want to point out is all of these ratios are intertwined with each other. If you had a really complicated trigonometry problem with lots of sines and cosines and tangents and secants and cosecants, you can rewrite the problem to use any one of the signs that you want. It's like saying, could you do all the math you need to do if the 5 was broken on your calculator? How would you get around not having a 5? You just replace it with 2 plus 3, or 10 divided by 2. Right? If the cosine button was broken on your calculator, or if you only had a sine button, you could rewrite everything in terms of sine, or cosine, or tangent, or any one of them. All right, you have 2 more problems on this paper, and then everything on the other side. Good luck.